Have you ever looked at a chemical reaction and wondered, why? Why do some just happen in a flash, while others do absolutely nothing? Well, today we're going to become chemical detectives. We're cracking the code on the invisible force that pushes and pulls electrons, something called electrode potential.
So to get our heads around this, let's start with a really simple but kind of puzzling little chemistry story.
Okay, so here's the mystery. Picture this. You take a simple copper wire and you dip it into a solution full of silver ions. Almost instantly, a reaction kicks off. You can literally see silver starting to coat the wire. But then, you take that exact same copper wire and dip it into a solution of lead ions. And, well, nothing. Absolutely nothing happens. It just sits there.
So what gives? I mean, it's the same copper wire. Why does one combination burst into action while the other is a total dud? This question, right here, is the key to understanding what really drives chemistry.
To solve this little puzzle, we need a way to measure that invisible push, that force that's making electrons jump from one thing to another. We need a ruler for the driving force of a reaction.
And that force has a name, cell potential. You'll see it written as E cell. But you're probably way more familiar with its everyday name, voltage. Yeah, that's right. It's literally a measurement of the energy behind moving electrons around. It tells us just how eager those electrons are to make a move.
Now here's where it gets really clever. How do you actually measure this stuff? It's not like you can just put a chemical on a scale and get a reading. It's a little trickier than that.
And here's the catch, the big problem. You can't measure the potential of just one substance all by itself. I mean, think about it. For electrons to transfer, you need a giver and a taker, right? So you can only ever measure the difference in potential between two things. It's always a relative game.
So if everything's relative, how do you measure anything at all? Well, scientists came up with this brilliantly simple, elegant solution. They all just got together and agreed to create a universal reference point, a starting line, and then they just assigned it a value.
And here it is. Meet our benchmark, the standard hydrogen electrode, or SHE for short. This is the universal yardstick. Every other chemical's potential, its push, is going to be measured against this one standard setup.
And what magical value did they assign to it? 0. Exactly 0 volts. Now get this. The SHE isn't measured to be 0. It is defined as 0. It's like the sea level of electrochemistry. Everything else is measured as being either above or below this one single point.
So what does having this 0 point do for us? Well, it's a game changer. It lets us create a kind of power ranking for all these different chemical reactions. Now we can measure everything against our new baseline. This basically gives us a leaderboard, a league table for chemicals, ranking them on how badly they want to pull in electrons, their strength as an oxidant. This hunger for electrons all comes down to their atomic structure. Some elements are just naturally greedier for electrons than others.
And here is that leaderboard. Look at this. Way up at the top, you've got fluorine, the undisputed champion of grabbing electrons, with a huge positive value. Way down at the bottom, you've got lithium, which is the weakest. And right there in the middle, see it? Our reference point, hydrogen, at a perfect 0-0. And hey, look who's on the list. Silver is positive, but lead is negative.
Okay, we are ready. We have our leaderboard, we have our suspects. We can finally use this data to go back and crack our copper case once and for all. All we need now is the formula.
And here it is. It's actually super simple. The total cell potential is just the potential of the cathode, that's the part getting the electrons, minus the potential of the anode, the part losing the electrons. And here's the golden rule. If your answer is positive, the reaction just goes. If it's negative, it's a no-go. That's it.
All right, let's put this formula to the test. First up, our reacting pair. Copper wire in that silver solution.
Okay, so in this reaction, the silver ions are gaining electrons, so that makes them the cathode. The copper is losing electrons, making it the anode. So we just look up their values from our leaderboard. Silver is a positive 0.7996, and copper is a positive 0.34. Now we just plug those right into our formula.
And what do we get? Positive 0.46 volts. It's a positive number. And what does positive mean? It means the reaction is spontaneous. It happens all on its own, which is exactly what we saw. Boom, case 1 closed.
Okay, that was satisfying. But now for the other half of the mystery. Let's see why nothing happened when we put the copper in the lead solution. Let's run the exact same calculation. So in this scenario, we're testing if lead ions can take electrons from copper. That would make lead our cathode and copper our anode. We look them up on the chart. Lead has a value of negative 0.1262 volts. Copper is still that positive 0.34, so let's do the math. Cathode minus anode.
And there it is. The answer is negative 0.47 volts. A negative result means the reaction is non-spontaneous. It just won't happen. The numbers don't lie. This is the solution to our mystery. We just predicted reality with some simple math.
And what's so incredibly powerful about this is that it's not just for explaining things that have already happened. We now have a tool that lets us predict the future for countless other chemical combinations. For example, let's try a quick one. Will bromine react with iodide ions? Let's see. You find their potentials, you run the numbers, cathode minus anode, and you get a positive answer. So yes, it's spontaneous. Just like that, you've become a chemical fortune teller. You can predict what's going to happen.
So we've cracked the code. We understand the fundamental push and pull of electrons. But take a step back and think about this. This isn't just some abstract concept from a textbook. This exact principle, this is what runs every single battery in every phone, laptop, and electric car on the entire planet. So, the next time your phone screen lights up, you'll know exactly what's going on under the hood. It's all thanks to a carefully predicted, perfectly spontaneous chemical reaction.